Nanowarming, the future of cryogenics, revolutionizing organ preservation. Imagine this. You freeze a strawberry. You thaw it. What do you get? Mush. Now imagine doing the same thing to a human organ or a brain. This is where most conversations about cryogenics quietly collapse. Because here's the uncomfortable truth. Freezing is not the hard part. Waking things back up is. For decades, cryogenics has been sold as a problem of cold. In reality, it is a problem of heat, physics, and structural damage. And until recently, that problem looked almost unsolvable. Let's get something straight. Cells don't die because they are cold. They die because ice formation breaks cells. When water freezes, it forms crystals. Crystals expand. Crystals puncture membranes, organelles, and proteins. So modern cryobiology doesn't try to freeze life. It tries to avoid ice entirely. This leads to a key idea: vitrification. Vitrification means turning biological tissue into a glass-like solid without ice crystals. No crystals, then no mechanical shredding. To do this, we use extremely fast cooling and cryoprotective agents, chemicals like DMSO, glycerol, and newer mixtures. For cells and embryos, this works beautifully. That's why IVF clinics freeze embryos every day. But now scale up. Freezing a single cell is easy. Freezing a human organ is a nightmare. Why? Because physics does not scale politely. Large volumes suffer from uneven cooling, uneven warming, thermal gradients, mechanical stress. You can vitrify a large tissue, but the moment you try to warm it, cracks appear. Ice recrystallizes. The structure fails internally. This is not biology failing. This is materials science failing. A vitrified organ behaves more like glass than flesh. And glass does not like being heated unevenly. For decades, the dominant strategy was simple. Just heat it from the outside. Warm baths, warm fluids, external heaters. This works for small things. But for large vitrified volumes, it's catastrophic. The outside warms first. The inside lags behind. Stress builds. And just like a glass cup under hot water, it fractures. This single problem destroyed countless promising cryopreservation attempts. And for a long time, there was no obvious way around it. Until someone asked a different question. Instead of heating from the outside in, what if we heated everywhere at once? This is the idea behind nanowarming. Here's how it works. You perfuse the tissue or organ with magnetic nanoparticles, typically iron oxide, already used in medicine. You apply an alternating magnetic field. The nanoparticles heat up due to magnetic losses. Heat is generated inside the tissue itself. This is called volumetric heating. The consequences are enormous. Dramatically reduced thermal gradients, faster, more uniform warming, suppressed ice recrystallization, fewer fractures. This is not science fiction. This has been demonstrated experimentally, including in peer-reviewed studies published in Nature Communications. For the first time, warming stopped being the weak link. Nanowarming matters because it solves the correct problem. Cryogenics was never blocked by lack of cold, lack of storage, lack of imagination. It was blocked by thermodynamics. Nanowarming directly attacks heat transfer, phase transitions, mechanical stress in vitrified matter, and most importantly, the remaining problems are engineering problems, not conceptual ones. Things like nanoparticle toxicity, uniform perfusion, particle removal after warming. These are hard, but they are solvable. This is why nanowarming has a high probability of real-world impact in the next 5 to 15 years. Nanowarming doesn't work alone. It works best when combined with other advances. Next-generating cryoprotectant agents, CPA, modern CPA mixtures aim to reduce toxicity, maintain vitrification, stabilize membranes and proteins. Less chemical damage upfront means less repair later. Ice recrystallization inhibitors, IRIs. Even tiny ice crystals can grow during warming. IRIs, often polymers, prevent this growth. They don't stop freezing. They stop damage amplification. Classical thermal engineering. Yes, boring engineering still matters. Better models, better control ramps, smarter perfusion. Many failures are not exotic. They are basic heat transfer mistakes. This is where hype usually enters. Nanorobots that repair membranes, rebuild proteins, fix synapses, reconstruct brains. In theory, fascinating. In practice, we currently cannot control matter at that level, do not understand biological correctness well enough, cannot coordinate trillions of molecular agents. Nanorobots are not the next step. They are the last step. A horizon of 50 to 100 years, if ever. Let's be brutally honest. Here's what actually has a chance. Nanowarming has a high chance in the next 5 to 15 years. Better cryoprotectant chemistry has also a high chance, but in the next 5 to 20 years. Ice recrystallization inhibitors has a medium chance in the next 10 to 20 years. Post-thaw biochemical repair has a medium in the next 15 to 30 years. Genetic cryotolerance has a low chance in the next 20 to 40 years. Nanorobotic repair has a very low in the next 50 to 100 years. The future is layered, not magical. Here is the key insight most discussions miss. Cryogenics fails when we treat it as biology. It progresses when we treat it as physics first. Heat, phase transitions, stress. Solve those and biology suddenly becomes manageable. Nanowarming doesn't promise immortality. It promises something far more important, a path forward that actually respects reality. Cryogenics is not about cheating death. It's about how much information you can preserve in matter. And information hates chaos. Nanowarming is the first tool that seriously reduces chaos at scale. Not the end of the story, but the first chapter that truly works.